Good morning. This is Lab 6. Now, if you haven't read Lab 6, this is going to be completely confusing to you. So, and I'm not going to stop and go back. You're going to have to catch up. We're going to do, this lab is 2 distinct parts. It has the same concept, but it's 2 distinct parts. I'm going to write the first equation up here for the time period for a spring. Now you saw this equation in lab 1. So we have the time period is 2 pi times the square root of m over k. Now, if you recall, in lab 1, we plotted a bunch of points and ascertained what k was. We're going to do exactly the same thing here. And I'll write this for, I'll do it for the spring, and then I'll do it for the pendulum. So now we're going to say t squared is 4 pi squared over k times m. So you are going to plot m versus t squared. You're going to put some data points, and then you're going to fit that line. The slope of this line should be 4 pi squared over k, because that's what this coefficient is right here. Okay? That's pretty easy. We've done it once already. We're going to do the same thing for the, oh, by the way, that means you're going to need some value of k for your math model. All these scattered points are your data model. Math, let me write that. Math need k, and t, this is data, need m t squared pairs. Okay, pretty simple there. Now, for the pendulum, we're going to say t equals 2 pi square root of L, I'll make this a capital L, over G. And I'm going to say t squared is 4 pi squared over G times L. And we are going to plot L, just like the mass, and we're going to plot t squared right here. We're going to put on data points, and we're going to figure that out. And the slope here should be 4 pi squared over G. So this is the math. You don't need G, but if you have G, if you have to calculate G, you can get it off that slope. And this is the data. And that's the start of the first part of this experiment, how to understand the math. Any questions on that? And I'll stop right here. Okay, now I'm going to show you how to do the first part of the experiment. So remember, it's 2 parts to each one of these parts. Wow, said that a lot of times. Let me say this. We need to ascertain the spring constant, which is a control variable for the first part. So the way we're going to do this is very simple. We're going to measure this spring. Now we can measure it from the table up and then look at the difference in it. But we need to know what the relaxed length of the spring is. Okay, that'll be a Y0. So that's relaxed. Now, I'm going to hang a mass on this. In this case, it happens to be 100 grams, but I think in the experiment we start with 50. And you notice that it's stretched. When I let it sit, I need to know what the difference is from top to the bottom. Okay, so this is Y2. The first one was Y0. We'll call this Y1. And we'll subtract them. Hooke's law says F equals Kx. I can ascertain what K is. Okay, piece of cake. And I can do this for a couple of these if I want. I can add some more weight to it. And we can stretch it a little more, you see. And I can add some more weight to it, and it'll stretch some more. Okay, so F equals Kx. We're going to determine that K. Now, once we have that K, we have the control variable. You should be able to go to that first equation and use that math model and say T equals 2 pi square root of m over k, and plot that. Or you can square it. It's preferable if you square it because then you'll have a straight line. It's easy to plot. And that's all I want to say right now for establishing the control variable. Okay, now I'm going to show you how we do this first part. You've already established a K for the math model. Now, if you read the lab experiment, it says determine the period using a 50-gram mass set in motion and do this for 10 complete oscillations. Okay, so we're going to do that. And then it says increase it in increments all the way up to 300, 350, 400, somewhere in that neighborhood. And we'll have a set of data points. So the way you do this is you hang a mass on here and you let it go to equilibrium. And then you oscillate it. Now, remember, the whole time we're doing this, we're measuring these things. So I'll just put this metric stick here. And you can see somebody's going to measure the bottom and somebody's going to watch the top. And you can do this real easily with another ruler, or you can do it with a straight edge of some kind. And you just keep moving it up and you move it down. So while you're doing that, somebody's timing it, you end up with 10 oscillations. And you can calculate the time period. Now, you don't have to calculate the time period. You don't need to right now. We're gathering data. So we're gathering a mass versus a time period. And then we'll insert that onto a piece of graph paper. We'll square the time period, leave the mass alone. We'll have a straight line. We'll compare that to the math model. Okay, so we're going to do that for 50-gram increments. So we'll just keep adding 50s to this thing, and we'll let it go. And we'll let it stop right about there. And then we'll pull it down. We know the bottom, and now we know the top. Okay, and that's all we have to do. And I'll give you the data for the experiment when we get done here. So that's pretty simple. Now, why are we doing that? Well, let's take a look at this. Okay, we're going to have a set of data points that are mass versus time squared. We'll plot that. Okay. What we're ultimately looking for is to write the equation. Now, what's the equation look like? Well, the equation looks like y equals a amplitude. Now the top to the bottom is 2a. So a is really from the 0 point back up or the 0 point down. Okay, but that's A. Cosine omega. Now, how do we get that omega? Well, remember, time is the inverse of frequency. Okay, so we got that. Now, frequency times 2 pi, I have it written here, I want to read it, I always read it upside down. So omega is 2 pi f. So once you establish the time period, you have f, and you multiply by 2 pi, you have omega. Now you have the equation. Y equals a cosine omega t. Okay. Now, if you weren't sure of that, you'd say 2 pi in frequency. 2 pi's in radians, frequency is 1 over seconds. 2 radians per second is what omega is. So, again, units will save you here. Okay, and that's all I want to say for that part of the equation, or that part of the experiment. Okay, for the second part of this experiment, I modify this a little bit, and I'll show you what I do as we go along. The first part is we want to ascertain that the mass is not a variable affecting the time period. Okay, so we're going to, I believe I have 3 different lengths on this string. This is representative, it's not exactly, but I've got 3 lengths. So I'm going to take the mass of this first weight. This first weight is probably going to be, let's see, what do I have for it? I think I have 100 grams. Okay, so I'm going to put it in motion and time it. Okay, now the experiment says time this thing for 30 cycles. Okay, so we'll get pretty accurate on the period of this the pendulum swinging. Then, without changing the length, I'm going to add some more mass to it. Okay, and I'm going to let that swing. And if you're astute, you'll see that the period hasn't changed because I didn't change the length of the string. Okay, and it won't matter if I come out a little further because it'll go faster as it goes through, but the time period will still be the same. Okay, so that's essentially this experiment in a nutshell. Now we are going to do this with 3 different lengths, okay, and we'll do the mass. We do the mass for both of them. We do 2 masses. And what you find out is that mass doesn't matter, okay? Because look at the equation. T equals 2 pi square root of L over G. There's no mass in that equation. Doesn't matter. So we'll do this with a couple of shortened lengths just to show you. Okay, now there's a shorter length, and you can see the period gets much quicker. Okay. Now I don't have any extra that I can add to it, but we could take another loop, put it in here, and it gets even shorter. Okay, so quicker period, and that's all I want to show you on that. I'll give you the data as we go along, and that's it.